Good morning, everyone. Welcome to the fourth and last day of 2022 Tripods Winter School and Workshop on interplay between artificial intelligence and dynamical systems. So today we are going to have a practicum session, so different from the previous days. So the topic of the practicum today is about supervised learning in function spaces. And I'm very happy to introduce our speaker today, Professor Perdikaris. Paris is an assistant professor in the Department of Mechanical Engineering and Applied Mechanics at University of Pennsylvania since 2017. He received his PhD in applied math from Brown University in 2015. Before joining UPenn, he was a postdoctoral associate at MIT. His current research interests include physics-informed machine learning, uncertainty quantification, and engineering design optimization. So with Paris, we have also two of his PhD students, Jacob Seidman, who is a sixth-year PhD student of applied math at UPenn. His research interest is about optimization, optimal control, and machine learning for functional data. And we also have Georgios Kissas, who is a fourth-year PhD student of mechanical engineering at UPenn, and his work focuses on developing methods for operator learning, physics-informed deep learning, and data-driven medical diagnostics. Paris, thank you so much for accepting our invitation. We are very excited to have you here. Please.
Thank you very much, Maher, for the introduction. Thank you very much for the invitation to you and the rest of the organizers. It's been a really interesting week attending the workshop, and today is a great opportunity for us to present some recent work of ours and others in this topic of learning, supervised learning in function spaces, or operator learning, as we refer to, which has emerged as a powerful tool over the last few years for analyzing functional data by learning maps between infinite dimensional function spaces. So that takes us a little bit beyond the classical paradigm of machine learning, where typically we learn functions mapping vector spaces. And now we're sort of abstracting this notion to learning operators between function spaces. So today I'm very excited to share the stage with students Jacob and George, who spend a lot of time over the last few years working in this area and getting familiar with the literature and contributing new techniques. So we have organized this workshop in 4 parts. So we're going to have a long day ahead of us, starting from some basic introductory notions of what is functional data and what could be potential applications, posing the problem of supervised learning in function spaces, and then going over a literature review and sort of giving you a taxonomy of different approaches ranging from parametric to non-parametric approaches for tackling this problem. We'll also go over through applications highlights, and then the tutorial is designed to sort of put equal emphasis on the methodological aspects, but also on the implementation and sort of hands-on aspects. So every part, especially part 1, part 2, and part 3, will be accompanied with a hands-on coding tutorial, starting with an introduction to Jax, which will be the framework of our choice for implementing all those methods in part 1, and then moving to part 2, where we're going to focus on existing techniques that have enjoyed success in the literature, starting from deep operator networks or DeepONets, including the formulation aspects, theory, and implementation towards the end, moving to neural operator methods with a particular focus on the Fourier neural operator technique, also providing background on theory, formulation, and coding aspects. And then we'll move on to more advanced topics towards the end, introducing some new attention-based architectures for operator learning, and we'll show some applications highlights to problems related to optimal control and climate modeling. At the end, we also hope to have some time to open the floor to discussion, highlight some open challenges, and interact with the audience. Just a quick note to the audience, please post your questions, use the chat to post your questions. There will be breaks between the different parts. You can also go to this link that we have just shared also in the chat, or scan the barcode on the slide. That will take you to a landing GitHub page where we have uploaded all of our slides and our coding tutorials. And you will see basically how the tutorial will be structured. So please post your questions in the chat, and then there will be breaks between the different parts so we can spend some time to answer your questions. And again, towards the end, we hope to have some extra time to have a more open discussion on the topic. So I hope you enjoy what we have prepared for you and you find things useful. And now I will be giving a pass to Jacob to get us started with part one. So I can stop sharing and Jacob can pick it up from here.
Thank you, Paris, and thank you, Mahir, again for hosting us. This is a very exciting opportunity to share with everyone some work that we're really excited about and find very interesting. So the starting point by means of introduction is the typical scenario that everyone is probably familiar with, which is machine learning for finite dimensional data. And what do we mean by finite dimensional data? That means that our data points are typically given as vectors in some finite dimensional vector space. So the classic example of, let's say we're classifying MNIST digits. Each picture is a pixel map, and for every pixel in the grid, we have a value. And so this very naturally is identified with a vector in R to the 784. So I have 784 numbers that exactly define my input data. And the output in the case of classification would be a one-hot encoding of a label. And this very naturally has the structure of an element in a 10-dimensional vector space. Moving forward to functional data, if we're dealing with things in the physical world, we often kind of have this baseline assumption that the physical world is fundamentally continuous. This could mean continuous in time. So if we're examining the trajectory of some dynamical system, that trajectory itself as a data point is naturally identified with a curve from some continuous time interval to some state space, depending on the system that we're measuring. Similarly, we can consider data, which is a function of space. This could be measurements over some continuous spatial domain. Maybe we're looking at the flow of a fluid inside of an artery. Maybe we're measuring things over the surface of the Earth. But in the real world, there really does exist a value at every point along a continuum modulo, philosophical considerations about quantizations of things. Often we really do view the world in this continuous light. And with the power of cheaper sensors and more sensors, we kind of are approaching, in some cases, this limit of really this continuum of data for these applications. So when we talk about functional data, there's this shift of saying a single data point is a collection of pixels as a picture to the data point itself is a function. And this idea seems like a bit of a jump, but there are some simple examples that actually bring this very close to what we know. For example, a vector in a finite dimensional vector space such as Rn actually can be thought of as a function. It's a function from a finite set of indices, in this case 1 to n, to the real numbers. Because we only need finitely many numbers to uniquely identify one of these points, we say that they're inherently finite dimensional. We only need finitely many numbers to describe them. However, if we move to a functional data point that exists over a continuum, for example, we can consider the temperature or the pressure field over the surface of the Earth, we're no longer able to describe this single functional data point with finitely many numbers. And in that sense, we would say that this data point, this function, lives in an infinite dimensional space. There is the structure of a vector space for functions like this because we're allowed to add them together, but we can't identify them uniquely with finitely many numbers. So we have to change the paradigm under which we try to do learning on these spaces. And so this is a nice idea, but it seems kind of odd to pose initially. If we're talking about creating a map between a collection of pixels, finitely many, and a one-hot encoding of a label, we are familiar with several kinds of architectures to do that. We can use neural networks, whatever your favorite class of parameterized functions from one finite dimensional vector space to another is. But we need to start thinking about how we actually can apply this to act on functions themselves. And so the first thing we might think of is, well, given that we know how to do this on finite dimensional vector spaces, why don't we take the measurements that we have of these functions? Maybe there's a lot of them. Maybe I have 100,000 measurements per curve, but that then still stacked together as some vector in R to the 100,000. And for the output function, if we're trying to learn a function-to-function correspondence, we could do the same thing. And then we appeal to all of the machine learning tools that have a history of performing decently well with enough data, multi-layer perceptrons, convolutional networks, recurrent networks, whatever your favorite model is. And we could apply this directly to the discretization of our data and hope that with enough data, maybe this would give us decent performance. However, there are some drawbacks to using this approach. The most important one is that we end up being completely constrained to that choice of discretization that we made in the beginning. If we take our continuous function here, everyone can see my mouse? And we choose to discretize it along these points and then consider each one of these as an input to a standard, let's say, feed-forward neural network. If at any point I get another data point in my input that does not lie exactly along one of these locations, or I lose one, or I have a different number of points, same thing with the output side, the model that I might have already trained, spent a lot of compute resources to get decent performance on this discretization, is now totally useless for this new data point. The only option is to either totally throw it away, not use it at all, or start from scratch and I have to train a new model, because if I discretize first, the architecture is inherently defined by where these measurements are taken. And so in this sense, we haven't really learned anything about the function itself. We've just learned something about the discretization of the function. So what can we do instead of this? The overarching philosophy of operator learning and learning on function spaces is, instead of discretizing first and learning a function of the discretization, we stay at the level of the function spaces for as long as we can and try to learn an operator between the curves directly. And if we do this properly, then we haven't tied ourselves to any particular discretization, and a trained model, if we've done this correctly, can be deployed for all kinds of different measurement schemes effectively. So the immediate, thing one might think of when you hear this idea is, this is a great idea on paper. We'll learn operators between functions, but computers don't get to take continuous data. Computers take finite lists of things. This is all going to be implemented on some machine. So I don't understand how we're avoiding this problem of discretization. Everything needs to be discretized at some point. Our measurements themselves are still fundamentally discrete. How can we learn operators between curves? And the main idea is that we wait until the very, very last second to choose our discretization. So by mathematically formulating the model at the level of these function spaces, then when we get measurements and we arrive at the point where we need to deal with discrete data, instead of formulating the model on the discretizations, we take a discrete approximation of the infinite dimensional model that we have formulated on paper. And so in doing this, we're able to handle different discretizations based on the measurements that we receive, because they're all approximating the same model at the level of function spaces. And we'll see examples of this going forward. So why is operator learning useful? I've motivated this a bit earlier in saying that there's functional data that exists in the world, but what kinds of problems would we actually use this for? Some examples are, let's say we have a dynamical system described by an ODE, and it has some kind of feedback control input. Maybe we want to design this, maybe we want to understand what the trajectories of the system will be for different control choices that we can make. We could use operator learning to directly learn the mapping between the control function to the trajectories of the dynamical system. And yes, classically, there's a lot of work on numerical integrators for such systems. It's not that we don't have other ways to solve this problem, but if we can create a computationally efficient operator learning model, after we've paid this upfront cost of training it, the forward evaluation of learning, of evaluating the trajectory of the system from its control input can be very, very fast, faster than the traditional numerical solvers potentially.
One quick question, Jacob. What is X in this notation here, U of X?
Yeah, so in this notation, X would be the state of the system, and T would be a time variable. So we'd be learning a function over the state space, some kind of feedback controller, so and associating to it. Go ahead.
If X is a state, then what is S?
S is the solution of the dynamical system. So S is a curve that is parameterized by time that lives in the state space. So we can think of this as a mapping from R to RD, where D is the dimension of the state space.
Thank
you. So we can do the same thing with PDEs that we can with ODEs. We can consider our input to be some initial condition of the PDE, a forcing term, a boundary term, and to it we can associate the solution of the PDE. This would be some kind of time-varying example where y is a spatial variable and t is a time variable. And again, there exist numerical solvers to do this classically, but for more complicated systems, we know that this can be computationally expensive. It requires many iterations, might or might not be stable under different circumstances. And if we propose a good operator learning architecture that with a reasonable amount of data can learn this correspondence, the forward evaluation to the solution can be very, very fast. And this can be incredibly useful in design applications, anytime you would want many forward evaluations of your PDE quickly. And more generally, there might be scenarios where we don't have a governing law for the dynamics of some system in the world, and we treat it more in the machine learning black box sense of, here are some functional inputs, here are some functional outputs, I want to learn the correspondence between them. Perhaps this is climate measurements over the surface of the Earth. I have measurements of some temperatures and I want to correspond them to some pressures. There maybe is some underlying law that governs that, but perhaps it's very hard to write down, or we know it's only an approximation to the truth. And instead of explicitly modeling some residual to try to get it in a closed form to describe with the master equation, the dynamics of the climate over the Earth, we'll do the machine learning thing and just learn this black box relationship between them so that we can make predictions and use that to inform our decisions. So at this point, I want to set up some notation that we're going to use throughout the sessions today for operator learning. So we'll consider our input data points, which again are functions. Each data point itself is a function, as being a function from a domain calligraphic X in some dx dimensional space to some du dimensional space. So the dx here refers to the dimension of our argument x for the input function. So we'll sometimes call the input function location. And du corresponds to the output dimension of the function u. In general, we will consider this domain to be compact because it's theoretically convenient for proving things. And we'll also consider these functions to be continuous. On the other side, our output functions are from domain calligraphic y, which contains points y in a space that has dimension dy. And the output of these functions will have a dimension ds. And we'll refer to the argument of our output function sometimes as a query or a query location, because the idea will be we'll give our operator learning architecture an input function, and then we'll want to query things about the output function. We want to know what the value is at particular locations. But throughout the talks, we will, to the best that we can, stick to this notation of u will be the input function, s will be the output function, x will be the argument of the input function, and y will be the argument or the query of the output function. And at this point, we're in a situation where we can formally pose our supervised operator learning problem. And you'll notice this is totally analogous to the typical supervised learning scenario in finite dimensions, except now everything is a function and lives in a function space. So we'll assume that we're given n pairs of input and output functions, and our job is to learn an operator that associates to each input function the corresponding output function. And the way that we'll approach this in the later talks is usually through empirical risk minimization. We'll form an empirical risk out of this data set. We'll have an architecture that depends on some finite dimensional parameters, and we'll use an iterative procedure to update those parameters to minimize the empirical risk, exactly as we do in the finite dimensional regression case. So operator learning isn't a totally new idea. In the past, 2 or 3 years, there's definitely been a lot of very new and interesting and successful work that has come out. But people have thought about these ideas before. So in particular, there are some non-parametric methods that you can apply. For those of you who are familiar with kernel methods and reproducing kernel Hilbert spaces, there is an analogous theory for doing this over spaces of functions or arbitrary Banach spaces. It behaves pretty much exactly as you would expect from the finite dimensional or scalar case, which is that you have some kernel that takes 2 input functions and associates to it a linear transformation on the output space. And we have a representer theorem that says, in reproducing kernel Hilbert space defined by this kernel, the solution to a typical ERM problem will take this form. And all that you need to do is learn these representing elements, which here are, instead of being scalars as they are in the scalar case, are elements of the output space. We're not going to focus on this formulation too much, but just wanted to bring it up for those of you who might like this style of a learning method. And here is a very good reference from 2016 that explains the theory and does give some applications as to how this works. What we will focus on are parametric methods. And by parametric methods, we mean methods that will depend on a finite dimensional set of parameters that will then update iteratively, similar to how neural networks would work in the finite dimensional case. And we're going to focus on three main approaches, which will be split up over the remaining sessions. The first is the so-called DeepONet, which was created out of Brown. The next is the neural operator, coming out of some folks at Caltech. And lastly, we'll present a new architecture based on an attention mechanism that Paris, George, and our collaborators at Penn have recently developed and we're very excited about. And with that, next we have our introduction to Jax, which is a very interesting language. I think if you're not familiar with it, you might find it to be very useful. It's very fast, easy to vectorize things. And then after that, we'll go into the details of some of these new recent parameterized operator learning architectures. With that, I will hand it over to George. Are there any questions on this part?
Oh.
No questions? Here I have stop sharing.
We also have some time for questions at the end of part one, between the break.
Can you see my screen?
Yes.
Okay, let me do it again. Okay, cool. So let's start with Jax. What is Jax and why would we use it? Actually, Jax is a language that was developed by Google, and it has a NumPy-like syntax, and it is very easily vectorizable, and then you can run pretty much the same code on CPUs, GPUs, and TPUs, right? So it's very this could be like very useful for somebody that it's not, very good with high performance computing, but wants to scale code.
Sorry,
Right?
George, is it possible to zoom in a little bit just to enlarge, control plus the fonts? So,
yes.
Yeah, perfect.
Okay. Right. So let's start. This is some reference that you can read about DeepMind. They talk about Jax. They talk about real world applications that they are using Jax, like protein folding and stuff like that. And then this is the GitHub page of Jax that you can download it. And it has a lot of instructions about how to code stuff and how to install it in CPUs and GPUs, right? So what is the connection between Jax and NumPy? Okay, so Jax is essentially a NumPy on steroids, right? So there are a lot of things that they are going under the hood that we will explain one by one after another, one each time as we progress in the tutorial. And what I want to show you here is that it has some simple NumPy-like syntax, right? So first, instead of importing NumPy, you import Jax.NumPy. And then what you can do is like, you can create matrices like in NumPy, you can take the products like in NumPy, and here we will see some connection between NumPy and Jax NumPy, right? So which is faster? You see Jax is a little bit faster, right? So also you can plot your output vectors like you do in NumPy without any difference, right? The code is exactly the same. And the only difference now is that the basic structure of a Jax NumPy array is this device array instead of this ND array. So what are device arrays? Device arrays are pretty much some structures that are device agnostic, meaning that they can run the same thing on GPUs, CPUs, or TPUs. They have some other properties that they are a little bit more involved that you can read about here. They're lazy. That means that they give you back the values only if you ask for them. And then they are mutable. This is very important. Immutable means that you cannot assign values to them. So if I try to run this thing here, you will see that this will fail. I cannot assign values to them, right? What I can do is I can use some Jax the library functions that then I can assign values to them, right? You need to do it this way. So Jax, the whole idea of Jax is based on pure functions, right? What are pure functions? Pure functions are essentially functions that have, they have like, if you provide them the same input, they will provide you with the same output. And the most important thing is that they have no side effects, right? What does it mean? It has no side effects, right? That means essentially that you can, for example, you cannot print something. You cannot append, you cannot change the input. Also, you cannot change some global variable, right? So that means that whatever happens inside there, there is no connection to the outside, right? So why does Jax use these pure functions? So in order to answer this question, we need to go one bit further to talk about a little bit how Jax works. The way that Jax works is essentially that you have something that is called Jax PR. This is an intermediate language, which means that takes the Jax operations, so the code that you write, and translate it to some very simple intermediate language, which is called Jax PR. Also, you can read these references here in order to see how this works. And let's see first how Jax works for pure functions, right? Well, how Jax PR. So that means that you will provide a function, and then we will use this code here, and also this make Jax PR function to understand how this thing works, right? And this is very, very easy to understand, right? So you have this function here that takes two arguments, the first and the second argument. The second argument is applied with a Zine function and then multiplied by scalar 3, right? So we have two arrays like 8 and 8, and then we provide that to this function. And then we Jax PR it to see what's happening, right? So what's happening here? This gets argument A and argument B, and then applies argument Zine to argument B, multiplies it by 3, and then adds and returns. So this is this intermediate language that they are very simple operations, but also very, very powerful, right? We will explain why as we go forward. And also you can see this representation that it's a graph representation, which is exactly the same thing. Take a float 32, that size 8, Zine it, multiplied by scalar, right? Add another array, and then get the output. So how does this work for impure functions, right? So as you can see, this is an impure function. Why? Because I append to a global list, so there is a side effect. So what happens here? If we run the same Jax PR thing, you will see that there is no mention to this append function, which means that the global functions, these global functions do not translate to this intermediate language, which means that Jax don't trace them essentially. So let's see the same sketch, right? So for this sketch, you will see that there is no difference, nothing changed, right? So that means that we don't trace this operation, right? So this is not a bug. This is a design feature of Jax. So be careful, because if you write in pure functions in Jax, there is no guarantee how they will be translated in Jax PR, which means that there is no guarantee that they will work as you would like them to work, right? Okay, so Jax is very powerful because it provides us with 3 very basic but very important for machine learning function transformations. Okay, so this transformation take your NumPy-like syntax, and they do three basic things. One, it's something that's called JIT compilation, which means essentially that this uses just-in-time compilation, right? You can check here what this is, right? And executes your program on hardware accelerators, which means GPUs and TPUs. So this is very useful because you can scale applications without essentially changing a lot of your code, right? Run code, run on GPU super fast. Okay, so the other thing is automatic vectorization. That means that we take something that is applied to a single input and make it to apply to a vector field. It's like this makes batching easy in machine learning application. And the third transformation is essentially differentiation. Okay, so differentiation means that we can essentially do all this gradient-based optimization, like Adam, DD, all of that. We can very easily perform them in Jax. Okay, so we will start going over these function transformations one by one to essentially, see them and see how they work. Okay, so first you need to import the functions. So you import JIT, grad, and Vima, which is essentially the JIT compiling, taking gradients, automatic vectorization, right? And then let's see the just-in-time compilation. So we have this celu function here, right? This celu function is something that is an activation function commonly used in machine learning. And then, as you can see, I can run this celu function here and get some, some performance, some millisecond per loop, right? But then what I can do is also JIT the celu function, and then run it with JIT, and you see that the performance is much better. So you see that I have this the celu JIT X before I time it. This is called warm-up, and this happens because what JIT does is at first runs your code once and traces all the operations, right? Traces all the operations such that it finds a way to optimize them. Trace them then run them once, and then optimize them. Okay, so be careful because there is some overhead with JIT. So it's better to JIT only functions that you use a lot of times. Like if you have a training loop, the optimization steps in the training loop. And the other thing is that you would like to JIT as much of your code as possible, right? And there is a reason for that, that you can read here, because this is the XLA compiling. Okay, so, right, so be careful, because JIT requires all your arrays to have static shapes that you define from the start. You cannot change your shapes during the program, right? Because this is, and there is also a reason for that, that you can read in this just-in-time compilation in Jax, right? The other thing is that JIT is agnostic in the content of the array. So be careful, don't use control flow statements like if, else, and all that, because it might fail. Okay, so the second transformation is automatic vectorization, the Vima that we talked about. So what this does is, as we said, this takes like a function that is used to be applied for one thing and make it for a lot of things. So you can imagine that you can essentially take something that you are, some part of your code that you are using a for loop to perform, and instead of doing the for loop, throw away the for loop and you do a Vima. Right? And you can read this very useful references here. Also, there is something called PMAP that vectorizes across multiple GPUs, which is for very, very large batch sizes. It's very useful, right? So what happens here? So for example, let's consider this function, right? This tan-h function, right? And then what we can do is define some finite difference, central finite difference in this domain, which is n 500 points, right? So we can do a for loop and then find the gradient of this tan-h function, or we can do this Vmap, like apply this Vima transformation, which essentially takes this finite difference function and provides us another function that we can then provide x, which is the points, and then it can give, this gives us, right, essentially the gradient evaluated at the particular x points. Okay, and we can find the max error of that, and this is pretty much close to machine precision, right? The last transformation that we will talk about is the gradient. Okay, so this is Jax.grad. It's very useful because we can essentially, compute gradients, which is used in gradient-based optimization a lot. Right. So this is a very, very simple example. But we have some square, like x to the power of 2. Then we know the analytic gradient. So this grad square, what it does, it takes the square function and provides us a new function that we can evaluate it, let's say, at 4. Okay, so we evaluate this function at 4, and then we evaluate the analytical derivative at 4. And as you can see, we get something that is extremely close. Right? So, yeah. Remember that the grad function, if you are not provide the axis that you are trying to take, that you are taking the derivative of, it will always take the derivative with respect to the 0th axis of your function, right? So if we had x comma y, and then we provided this, it will take like the gradient with respect to x, not y. Okay. So the nice thing about Jax is that you can compose all these function transformations. So that means essentially that you can stack them together, right? So again, we can get this tanh, we can zit it, we can find this x, we can take points of that between minus pi and pi, 500 of those, and then we can vmap the operation of f. So we find all the tanh function evaluated at x points, then the gradient, the second gradient, the third gradient, the fourth gradient, and so on and so forth. All of these transformations are composable, right? Which is very nice because you can have like in a pins, like let's say application, you can have first, second, third derivative of PDEs. So you can use it like that, which is extremely, straightforward. So, and then we have another example. We plot what we've done before, this first derivative with finite differences, and we find that the two functions match pretty much. They're super close. The other thing now that we want to talk about Jax is the pseudo-random generators in Jax. So how you get pseudo-random numbers. So this is one of the major differences between Jax and NumPy. Okay, so Jax syntax is close. I mean, it's very, very close to NumPy in most cases, but this is an exception because the random numbers in Jax, they need an initial state, an initial random seed, such that they work. So if you don't, you need to provide always a seed. Okay, so you can read about the pseudo-random numbers here. So what happens? I can import the random library from Jax, and then I have some key, right? And then I have this random row.rng key. And then I provide, let's say, a key. Okay, I provide the random seed, and then this provides me with a key. Okay, so now there is some catch here. You need to be careful because when you set this key, you need to update it, because if you don't update this key and you get a random number with this random state, right? You will always get identical outputs. So you need to be careful to never reuse these keys, or I mean reuse them only if you want identical outputs. Which is cool because now essentially what you can do is that you can, all your random initializations in machine learning and all of these applications, they can be reproduced, right? I can have a particular key that I can, set it, and then all my initializations and all of my code is essentially reproducible. So when you want to sample a new random number, what you need to do is find another key. This is done by this random.split operation in Jax. So what does this mean? That you provide your old key, and this will provide you with a new key and a sub key, right? You can use your sub key to sample, let's say, a new random number, and you can use your new key to split again such that you can get a new key and a subkey, right? So you can get like one key and split it to independent keys, as many as you want, right? So that means that this has to do with how we handle states in Jax. And this we'll talk in the next tutorial because it's a little bit more advanced. Okay, so the question is, do they have any difference? No, they don't have any difference. They are equivalent random numbers. Okay, so and then you can split this key to as many numbers as you want. So for example, if I take this key and then I split it to 4 numbers, I can get, like you see, 3 plus the new key. Okay, so let's go over to something that is a little bit more involved. Okay, so that has to do with pi trees. Okay, so what are pi trees? When we talk about machine learning libraries and MLPs and machine learning models, what we have is always we have some parameters, right? And these parameters, most of the times most of the libraries that we use in Python, like PyTorch or TensorFlow, there are some attributes of the model. So if you define a class, then for example, this class has some parameters. These parameters are now attributes of the class, so you can recover them. But as we talked about in this tutorial so far, Jax handles, it handles essentially pure functions. So how are we going to do that, right? Because you cannot have this parameter stored in your model, right? So what you need to do is, and this is how we will define all our models, from the most simple to the most complicated. Every model that you define needs to provide you with 2 functions. One, it will be the initialization function, and the other one will be the apply function. Okay, so what happens in the initialization function? In the initialization function, you create your parameters, right? You define your parameters and their shape. The next thing you need to do is you need to store them in a specific structure that is called a pi tree. What is a pi tree? A pi tree is a list of lists or a list of dictionaries, or no, it's some complicated structure that Jax can handle. Okay. The other one, the function that you need, is essentially your apply function. What is your apply function? Your apply function is one simple function that applies your transformation. So for example, for a simple MLP, as you see here, this is the forward pass of the MLP. Okay, and then you can go in this, you can create like an initialization function, and this is like the initialization of the parameters of the neural network, right? And this, it's called here, and then this starts initializing your parameters, and then it creates a list out of that. Okay, so what's the next thing to do? The next thing to do is define a key, right? And then after you have this key, and then, oh, yeah, this would be a key. Right. So we create our key. We have some layers. Let's say it's 1, 32, 32, 1, and we provide it to the MLP. And what does it do? This takes this list here, and then it starts initializing the neural network. It takes it creates your parameters, and then it provides you back your parameters and the apply function, right? Okay, and then what we can do is that we can just create a data set, right? So we can test what we have done so far. As we said before, this Jax, the Jax language, what it does, it creates some intermediate language, which then takes such that it applies a transformation that they're written in the intermediate language. So let's see what in this structure, in these graphs that we have done before, let's see how this translates. Okay, so what it does is this graph here, what it does is it describes what happens inside the apply function, right? So you take like 132, so this is your parameters, so the size of the parameters. You take some x, so the input to your neural network, and then what it does, this 32 is your bias, right? You multiply, you add them, do some other transformation that we will talk about in a later tutorial, and then it goes to the next layer, and then to the next layer, right? And then to the next layer, and then this is your output. And this, essentially, this model now traces what happens inside your apply function. Okay, so now let's JIT it. Let's JIT it to see what's different, right? If we JIT it and then essentially do the same operation, right? You see that these two things are the same. What happens is that this becomes much, much simpler, right? This is a much simpler transformation because this JIT compiling is essentially a dynamic translation. It runs your code, as it runs your code, JIT is essentially finding which parts of your code are either repeated or they have some similar structure, and they batches them together, translate them to something that it's a language that's faster, right? And then what we can do is essentially we can write a loss function for that, and then the next thing that we can do is define an update function. The update function is essentially some, some gradient-based optimization that we have some learning rate, and then we have some gradients, right? We find some gradients. So this is very important. This is because the loss function, and take some parameters, right? Because this is a pure function, right? So you need to always give the pure function its state such that it can run. Okay, and then it takes some input, and then it takes the outputs and matches them together. Okay, so what this grad function does is that it provides you with another function, right, that also supports a pi tree, which has the same structure as parameters. That means that Jax can operate on very complicated structures with out of the box. This is very handy, right? And also what we can do is use this tree multimap function to essentially update all the parameters inside the whole tree. Okay, so what we can do, we can write this very simple for loop, right, to run this update function. And then after we do that, we can pull out the results, right? The results are okay. Right, so let's go over a more, we will have this prototypical example that we will use across all of these tutorials, and we will use it across all of this tutorial to such that there is some consistency pretty much. Okay, so now we have some data set, right? Some inputs and then some outputs. And then we need to create some code such that we can predict the input using the output. Okay, so what do we need to do that? We need to import the libraries that we are going to use. We need to define an architecture. We need to create a class that can fetch us many batches during training. So some examples that are different each time. Okay, so we need to have some function that can handle our training, initialization, and all the helper functions. Okay, and then we need to define a function that will reprocess the training and the testing data, and the main body of the function that will essentially call all the other things and manage all these operations. Okay, so let's start from this example. This is an example from physical applications. It's called the Darcy problem, which essentially is flow through a porous medium. Okay, so this is defined by this essentially this function, which is something like a diffusion equation, pretty much. And then we have some boundary conditions. So here V0 is this random permeability, S is the solution, F is essentially some forcing, X is the domain. Okay, so we have some boundary conditions like the Dirichlet-Neumann. So the Dirichlet conditions are essentially on the left and on the right, right? And then we have some Neumann conditions, top and bottom. Okay, so this is Dirichlet, this is Neumann. Right, so what we want to do is have some essentially measurements of the function on the input on a uniform grid. Then we need to find the solution, the output, again on a uniform grid. Okay, same grid. This is the finite dimensional learning, right? So we cannot change the resolution as long as we set it. Okay, so what we have is this is the norm. This is using the Neumann boundary condition, this G, and then this is the forcing term. And then we sample these functions from a Gaussian measure, right? So Gaussian random field, which is defined like that. Okay, and then, right, so we sample a lot of input-output pairs, right, along this X by NY grid. And then we solve it in Phoenix, this Darcy flow, and then we take the results and you know, push them, give them to the neural network so that it learns this solution. And this is done by this image-to-image regression, which is essentially this architecture. You start with larger, let's say, encoder-decoder architecture that it's symmetric, and this is how the Gaussian random fields look like, and this is how the output looks like. Right? So let's start. We start by importing some very useful libraries that we can that you will use in the whole thing, right? And then you can use this part of code such that you can import this Google Drive. You have a Google Drive about that contains the this data set. Then the next thing that we need to do is define our encoder and our decoder. Okay, so I will briefly go over this here because in the next tutorial, we will go in much depth of how this works. So for now, you can imagine that this is some convolution, the batch normalization, ReLU convolution. So it's exactly what you see, like this type of operation, convolution, batch normalization, and so on and so forth, right? And then these operations are done in serial. So the data set goes inside this encoder, it does this convolution, batch normalization, ReLU, and so on and so forth, right? And then there is the decoder. The decoder essentially does pretty much the same thing, right? But in reverse. Okay, so this serial, essentially what it does is it performs this function transformation one after the other. Okay, again, don't be afraid of that. We will go in the next tutorial and the next after that, and we will explain how this works in more depth, right? We will create our own transformations inside here, and then we will see how the stacks, the serial, essentially puts these things together. Okay, so not be afraid. Okay, so we have this class that generates essentially mini batches. So what does this do? This takes like the input and the target. So it takes two data sets, and then what it does is that it essentially it's initialized. So it saves these two data set, and then it takes some key, like we define it here, its first key, and then each time you call it, what it does, it takes the key, it splits it, and then after this, it gets an item, takes the key, split it, and then go to this data generation function, and then use this new key to make a random choice out of your data set. So go to your data set, let's say your batch size is 100, your data set is 1,000, takes 100 out of this 1,000 things, right? And then it chooses this from the inputs, it chooses this IDX, and then gives it back to you, pretty much. So this is how we will choose batches. Okay, so this is a class that contains essentially this main body of this image-to-image regression. And this class is initialized, then here we initialize the architecture, so this is encoder. What we will get is again an apply function and an initialization function. Okay, so the decoder, the same thing. Again, we will go over all those things one after the other in the next tutorial, so don't be afraid. I don't know if I have a lot of time, so we will go a little bit fast. And then if you have any questions, you can ask me. Every tutorial is structured such that whatever you see here is pretty much the same for every tutorial. So if you have some questions here, they will be answered in the next tutorial or in the next tutorial after that. So what is, for me, very interesting is that when you initialize this, you use this encode, the initializer encoder, so you define your parameters in their shape, you can use this -1 here in Jax. What does this -1 means? That -1 means vectorized. So that means that you don't need to set your batch size from the start. And this is very useful because having that things in mind, having in your mind that you can vectorize your model, so you can vectorize your operations. What you can do is write your forward pass for one, let's say, item, and then vectorize it. And then we will see in the next tutorial in the DeepONets how useful that is. Okay, so this is pretty much what happens. You get your encoder and then your output dimension. We will talk about how important this is in the third tutorial. This is essentially, it means what is the output shape of this encoder layer, right? Where you can define your optimizer, and then you can define your learning rate, you can define your decay, and then this is the this is the scheduler, and then you can have here your Adam optimizer, and then this will provide you some initialization, update, and get parameters. So that means, remember that the Jax functions are all functional. So that means that they cannot conserve their state. So at each time, you need to first initialize them, and then at each time you need to be able to get their state and update their state, because they cannot retain their state. So the get parameters is such that you get their state, and the opt update is such that you update their state. Right? So this is your loss function, which is essentially apply the first, the encoder, apply the encoder, and then this is your loss. And then this is your step, right? As we defined before. What it does, get the state of the optimizer, get your parameters, right? Define the function that is a gradient of the loss function, right? Remember, this again, this is functional, so you need to provide the state. Okay, and then you provide a batch, then this thing goes, computes this transformation, takes the gradient, and then updates the state of the optimizer, right? And then what we have is this training loop, right? Which is essentially does all this operation again and again and again. Okay, so as you see, we have JITted this operation, right? Because as we said, we need to JIT the largest part of the code. And this might seem small, but this is actually the largest part of the code, because when you JIT it, it starts JIT everything else, right? And then this is your prediction. You need a function such that you can make predictions. So you can essentially provide the parameters, you provide your inputs that you want to make predictions, and then this will provide you the prediction. Okay, and then we have added some helper function, which is essentially counts the parameter of the model. Right, so what do we have here? We have a dataset of this Darcy problem, and then essentially what we need is we have 5,000 input-output pairs, and this has like 256 resolution by 256, and we sample that. Let's say that we use a sample of 4, so this is 64 by 64. Okay, so we load it, we delete this structure because it doesn't have a lot of RAM. And then the next thing that we need to do is that we can plot one of those, two of those things to see how they look like. Right, this is the permeability, and this is the output. Okay, so the second thing that we need to do is that we initialize your model, right? Initialize your model, you count your parameters, about 600,000, not too many. Then the next thing that you need to do is that you either train your model or you load some saved parameters. Okay, so very important, these flat parameters here. If you see up here, I use this, where is it? Ravel pi tree. That means that you take a pi tree, which is a list of lists, and you essentially, what you do is you flatten it. So you need a way to flatten it and a way to put it back together. right? We flatten it, and this way you put it back together. So we have like a flattened tree, and then we put it back together to tree. And then here we make essentially some predictions. This is pretty much the idea. Okay, so we'll find this Y prediction, and then what we do is we run a loop, and in this loop we essentially compute the individual relative L2 error for each input-output pair. And this has a mean error of 1, and then the max error of 5%. Okay, and then this is essentially a function that you can use such that you can save your parameters, such that you don't need to run it again, because this model takes like a lot of time. Okay, so this is the end of the first tutorial. Thank you. I hope I was.
Right, so we finished actually ahead of time the first part. We have some time for discussion and questions. There is one question posted by Felix. Can grad be used in higher dimensions?
Okay, so yes, gradient can be used for functions that have a scalar output, right? But that doesn't mean that you cannot use it for functions that have vector inputs. So for example, that a loss function has like vector inputs and a scalar output, you can use it. It's very, very, very easy. And you don't need to have complicated things, right? It's like we said, yeah.
Just to dive a little bit on the details of this, so there is basically two modes, right? There's reverse mode, automatic differentiation, and forward mode. And which one you choose depends on the dimensions of the input and the output that the function you're differentiating has. So grad is actually used for scalar valued functions, but could actually have high dimensional inputs, and essentially performs reverse mode automatic differentiation, which is kind of the most common type used in machine learning, because typically we want to differentiate loss functions that are scalar functions of many, many parameters. However, you can actually, Jax provides support for forward mode automatic differentiation, and also support for vector valued outputs. In this case, you want to be building Jacobian matrices. And again, you can use forward or reverse mode differentiation to compute the Jacobian. So I can post a link in the chat that points you to more resources to learn about this. One limitation is when you start composing and you want to compute higher order derivatives, so you start composing those grad operations, obviously that might lead to some memory and computational bottlenecks, because as you compose, your computational graph gets sort of exponentially bigger. So computing high order derivatives is not straightforward using these operations. That being said, there are alternative modes for performing automatic differentiation, such that Taylor mode automatic differentiation that is more scalable to higher order derivatives. Yeah, Leo posted the link on more details on automatic differentiation using Jax in the general chat.
I have a high-level question. How do you compare PyTorch with Jax? Like, are there any functionalities that are present in Jax and you need them and they are not present in PyTorch?
Oh, okay. So, well, I mean, I think that PyTorch has the newest version has a lot of these functionalities, but in my opinion, Jax is a different way of writing code based on functional programming. For me, functional programming is clean, right? It's scalable. It's NumPy-like, so it's the Jax is easy to write. It's easy to understand, right? And then it's very easy to write very scalable code without weird tricks or something. That's my opinion. So I'm not an expert in PyTorch, but I would say that, I don't know if there is some metric to compare them, but in my understanding, Jax is.
I think maybe just to add on this, a high-level answer is that the functionalities are very similar. So I don't think there's things you could do in Jax that you cannot do in TensorFlow or PyTorch. The performance can also be similar if your programming skills are advanced enough. The key difference, I think, has to do with the distinction of whether you're a developer and you really want to use the code for research purposes and you want to write things from scratch and fully understand what's going on, versus being a user where you don't mind taking black box components that somebody else has developed and putting them together. So I think TensorFlow and PyTorch provide a lot of functionality for the user side of things. They have wrappers like Keras that make it user-friendly. They have a lot of support for, writing machine learning apps for mobile phones or iPads. So there is a lot of functionality towards the product side of things and the large-scale applications. But from the user point of view, Jax provides really convenient functionality for research purposes and development that allows you to write very transparent code, very reproducible, by the fact that you have full control on randomness through the way random number generation is handled. So for people that want to learn a framework focused for their own research, at least in my personal opinion, over the last 1 or 2 years that we've been using Jax, it really has enabled us to do things that were kind of hard to do before using TensorFlow or PyTorch.
Yeah, so that doesn't mean that Jax is not, you cannot write product level code, right? Because Google writes this vision transformer monsters in Jax. And
obviously it's a relatively newer framework compared to TensorFlow and PyTorch. So it's kind of like gaining momentum as we go. It seems like it's gaining a lot of traction, and in a few years might be overtaking the other two. We'll see how that goes.
Yeah, it's most of a programming style. I mean, I find Jax very, very intuitive. You write the math, you write the code. It's pretty much.
I guess the learning curve also is a bit easier because it really looks like NumPy. So if you know some basic Python, you can easily switch to use that. Any more questions? There's a question. Any thoughts on differences, advantages, drawbacks compared to Julia? I think that's a great question because Julia is also gaining a lot of traction within the scientific computing community. And I think it offers a lot of convenient tools and a very nice ecosystem for scientific computing. I would say that Jax is more geared towards machine learning and the functionality it offers. It's really centered and focused on machine learning type of model development, which I guess Julia sort of still lags behind in terms of how easy it is to use multiple GPUs. And although Julia is sort of getting up to speed in that front as well. So I would say Julia is a fantastic ecosystem for scientific computing, whereas Jax is more for machine learning applications as of now. Is there any documentation on computational performance of Jax, PyTorch, and TensorFlow? I think there are some comparative studies one can find online. I don't have one coming to mind specifically right now, but I can look into it and share some links if you're interested. Any other questions? Says, hello, could be Jax an appropriate tool for implementing object-oriented programming in order to run them in GPU? And the answer is yes, absolutely. It facilitates object-oriented programming at a high level, so in Python, and it makes the use of GPU architectures extremely easy and convenient. So if you know some basic NumPy, basically now you can just use Jax instead, and you can run your codes on GPU with very little effort. And of course, it takes away all the complexity behind the scenes of writing code directly in CUDA. So it's very convenient in terms of utilizing GPUs and writing simple code that scales.